We're
Let's
live.
see. Yeah, we have to wait a little. On the other screen, I have YouTube. And do I see something happening there?
Hello, France. Bonjour, France.
I don't really see anything happen.
Well, I can see the comments now coming from YouTube.
Yeah, that's what I see on YouTube too. Ah, yeah. Yeah,
You
we're
good?
live. Yes,
Oh yeah,
we're
yeah.
live.
YouTube is 20 seconds delayed or something like that. That's probably why you're.
That's why I was confused.
Yeah.
Yeah, we're live.
Oh boy,
Awesome.
I'm coming to you at 720p.
We tried everything, but we
Yeah.
rather have you in 720 than
I actually
lagged.
prefer to be a little blurred out.
Well, we also would like to see your slides on the best resolution, so hopefully that will work out. I see Vincent joined the stream. Hi, Vincent. Good to see you,
Hello.
man. And yeah, I think
Now,
are we having all the people? Yeah, well, we're supposed to start, I think.
you're the one who I think who can click in my slides.
Yes, I will. Well, hello, world. Welcome to the Java Champions Conference. My name is Susanne Pietersen, and I am moderating this session. And Barry told me that he likes to be interrupted with your questions. So please drop them in the chat, and I will pass them to him. Experts predict that by 2035, quantum computers could crack today's encryption in just days. And our next speaker is here to show us how Java 24 is already preparing for that future. Here to guide us into the post-quantum era, please welcome Java champion Barry Bird.
Oh boy.
And then I go away.
There it is. Yay. Okay. All right. Well, post-quantum cryptography in Java. Welcome, everybody. Let me figure out. Boom. Okay. You should be able to see. Let me just double check. Yes, you can. Wonderful. Okay. This is all about me in gory detail. I'm the leader of a co-leader of two Java user groups. I've written a bunch of books, many of them about Java-related topics, many in the For Dummies series, and those books are really fun to write, so I enjoy doing them. And I write books that aren't in the Dummies series too. In particular, I have one called Quantum Computing Algorithms that I wrote, and that's where I'm coming from with this talk. So, the next slide comes with my disclaimer. My disclaimer for this presentation is that I am not a security expert. When it says post-quantum cryptography, I'm not an expert in cryptography issues. I'm more the person who wrote books and talks about quantum computing. So I'm coming at it from that angle. Now, I give you this disclaimer for two important reasons. One of them is don't take anything that I say during this talk as being actionable. I don't claim that your security will be airtight if you follow all the advice or all the comments that I have in this talk. The other thing is that since I'm really not a security expert, I imagine that there are questions you might have about Java security that I can't answer. Okay, you know all about it. Fine. Let's just go ahead and whatever questions you have, please interrupt me. I like being interrupted. It makes me feel wanted. Okay. So anyway, let's get started. The first thing that I want to do is just show you a picture of a laptop. And the reason I want to show you that is because I may, at times during this discussion, use the term classical computing. And when I talk about classical computing, that is exactly what I'm talking about. I'm talking about what we call the von Neumann architecture, the computers we have in our everyday world today. Those aren't quantum computers. What is a quantum computer? Well, a lot of quantum computers look like the picture on this slide. That cylindrical thing with all kinds of gold looking stuff on it gets dipped into a tank with um, with super cooled um, 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 helium or hydrogen or some other substance cooled to near absolute zero. And that's the only way that you can run a quantum computer these days, or it's the typical way that you run a quantum computer. You have the entire thing super duper cooled, and the super cooling avoids interference from any particles that would upset the delicate, extremely delicate balance that quantum phenomena have. So, what is quantum computing? It's a way of taking advantage of certain quantum phenomena, namely superposition and entanglement, very mysterious, very unintuitive phenomena. It's a way of taking advantage of those things in order to solve certain problems. Now, it's important to know that quantum computers are not general purpose computers. So somebody asks me, well, I have a quantum computer on my desk 10 years from now. And the answer is, uh, even if you wanted to run Excel or Word in with a quantum computer, even if you could do it, you probably wouldn't want to. These things, you don't program them by writing if statements and loops. No, what you do in order to program them is you take advantage of certain what I call coincidental correspondences between the way certain processes take place in the quantum world and certain other programs. So you take a problem that you want to solve, you map it to a certain combination of quantum phenomena, including superposition entanglement, and then you let the quantum phenomena go and ride and run and take place, and then you take the answer to that and translate it back into your problem domain. But those things that happen inside a quantum computer are nothing like the traditional tools, the traditional kind of logic thinking that we do in a classical computer. So, quantum computing is a world in and of itself. Programming a quantum computer these days means saying exactly what's going to happen to each qubit. And a qubit, a quantum bit, right? That's parallel to a bit in a classical computer. In other words, imagine that you were trying to program a classical computer, and you had to say what every single bit in the machine was doing. That's what you do with quantum computing. Right now, the quantum computers that we have, I can run one for free on the cloud that has about 10 qubits. If I want to pay money, I can run one that has 100 qubits, some. Um, if I know some people really well and I talk them into my being able to use their computer, maybe I can get up to 300, 400 qubits. You know, what would a classical computer with 3 or 400 bits do? Nothing, zero. But a quantum computer with 300 qubits starts to become powerful because the power of the computer rises exponentially with the addition of each qubit. So, when will we have a computer, a quantum computer, with enough qubits for it to be useful. And everybody that I talk to in the field says they think it's about 10 years away. Now, nobody has a crystal ball. I certainly don't. We can't ask ChatGPT when will quantum computing be useful commercially. Uh, but 10 years. I don't know. I'm just using it as a guess. So the question then is, what's going to happen in 10 years? Well, one of the answers is that malicious actors will be able to crack RSA in minutes. Yeah. I said that quantum computing is not general purpose computing. It can't solve all kinds of different problems. An arbitrary problem a quantum computer can't solve. But one of the things it can do really well is factor prime numbers. And factoring prime numbers is the heart of the RSA algorithm and many, many, many security algorithms. So why do I have a 3 and a 5 on the screen? Well, because just to remind you that it's easy to multiply two numbers and find out what their product is, but it's computationally difficult if you're given the product to factor the two numbers and find out where that product came from. Now, of course, we all know that 15 is 3 times 5. We don't have a problem factoring that. But when you're talking about enormous numbers, this becomes computationally intractable. And that's what makes RSA work. What makes RSA work is that I know where 15 came from, but I give you 15 or some very much larger number, and you will take trillions of years to factor it back into 3 and 5 or whatever large numbers we're talking about. I'm going to use small numbers in every illustration that I do because we don't want to deal with large numbers visually. Whenever you see a 3 and a 5 in this talk, picture two enormous numbers. Okay. Now, factoring prime numbers is one of the schemes. That's a scheme that RSA uses. There's another scheme that, for instance, Diffie-Hellman uses. I just want to illustrate what's going on there. Let's say we have the numbers 5 and 2 to the 4. Well, what do we do with that? First, we turn 2 to the 4 into 16. Again, remember big numbers, not just these small, tiny numbers. Then we divide 16 by 5, and we get a factor of 3 with a remainder of 1. And then what we report as public are these three numbers. And then we defy a malicious attacker to turn this back into 2 to the 4th. And it turns out computationally to be very hard to do. So the deal with these encryption algorithms, the public key encryption algorithms, is that there's something we know, like the numbers 3 and 5, and what we deliver publicly is the product of those two numbers. And since we know 3 and 5, we can decrypt a message sent by a sender. But a malicious actor knowing the number 15 can't do that decryption because they don't know how to factor the number 15. All right, let's move on. What kind of a problem? Oh, okay. First, I want to do this. Factoring is known to be computationally difficult. If you're into computational complexity, factoring is NP, non-deterministic polynomial, but it may not be NP complete. So there's no algorithm known for it that can be solved in n squared time, in n cubed time, in n to the fifth time, in n to the 100th time. If you know what I'm talking about computational complexity, you know that factoring is this makes factoring a really, really tough problem. But Peter Shor in 1994 revealed an algorithm that uses periodic sequences and a Fourier transform, which finds frequencies of periodic sequences, to ferret out the way you can factor two very large numbers, and to do it in minutes, hours, really quickly. And so we know that if we ever get a quantum computer with enough qubits, maybe 10,000 of them, maybe 100,000 of them, we know that if we get such a quantum computer, maybe 10 years from now, malicious actors will be able to break RSA within a practical amount of time, maybe minutes, hours, whatever. They'll take the time, they'll be able to do it. Of course, we don't know if there will be such quantum computers, but we want to guard against it now. And the reason we want to guard against it now is because of harvest now, decrypt later. So, what's happening now is malicious actors are saving our communications, our sensitive communications, within the hopes of, in 10 years, having a quantum computer that can decrypt them. Now, those sensitive communications, many of them might be stale 10 years from now, but some of them for sure won't be. And so, right now, the information that we're sending across various communication lines could be subject to malicious actions, even though quantum computers don't yet exist. We have to start worrying about this problem now. We have to stop using algorithms like RSA and start using more sophisticated algorithms. We can no longer depend on the difficulty of factoring large numbers. Okay, how are we going to do it? There are new algorithms developed in a competition, actually, from NIST, the National Institute of Science and Technology in the United States. And these algorithms depend not on factoring numbers, but on dealing with lattices. Now, the thing that you see in front of you is a lattice. What's a lattice? Well, it's a bunch of points in a space. Here we've got a two-dimensional space, but a typical lattice used for a problem like this has thousands of dimensions. Let's talk for a minute about spaces. For those of you who don't want to know the internals of how this algorithm works, you can turn off your volume for a few minutes. I just like to do this. I just like to know what's under the hood. Okay, what have we got? This is an ordinary grid. There's an x-axis and a y-axis. We have 2 points, if you will. One of them is at the I'm going to change to pointer options, laser pointer. Okay, one of the points is here, 1, 0, we used to call it, and another point is here, 0, 1. Now, if you add this arrow to the end of this blue arrow, you come up here. If you take 2 of these blue arrows and then add 2 blue arrows that are vertical, you come up here. What if we take 1 blue arrow that's horizontal and 1 copy of the vertical blue arrow going downward? Then we get to this point. Now, the dots that you see here are the only points that you can describe with these 2 arrows. So you really can't get here because you're restricting yourself to arrows of this length. This is an integer length arrow. So it goes to the 1 point on the x-axis, and this is an integer length arrow. So it goes to the 1 point on the y-axis. And if you combine these two arrows, you can get here, you can get here, and you can get here, but you can't get anywhere in between. And when we have a structure like that, these dots, we call these dots a lattice. The blue arrows are called basis vectors. They're basis vectors of what we call a vector space. And the red line represents the shortest vector that you can, the shortest arrow that you can describe using the two blue arrows. So using the two blue arrows, you can't go only up to here. You're not allowed to use half of one of the blue arrows. The shortest distance that you can go, this red arrow, is like that. So the question is, given two of these arrows, what's the shortest red arrow that you can describe? Let's march on. Let's say that instead of my arrows going to the 1 point on the x-axis and the 1 point on the y-axis, the horizontal one goes to the 2 point on the x-axis and goes to the 2 point on the y-axis. Then I can't even describe this dot here, the 1, 1 dot. My lattice now with those two vectors, with those two arrows, consists of these spread apart points. And the shortest arrow that I can possibly describe, or one of the shortest arrows that I can possibly describe, is this red one that's of length 2. So the question is, what is the shortest arrow that I can describe given two blue arrows? I want to give some intuitive feeling about how this problem works. Let's take a look at another example. Let's say that the two basis vectors, the two arrows that I'm allowing myself to use, are this one that goes to what we conventionally call the 5, 2 point, 5 points along the x-axis and 2 points up on the y-axis, and to this point 2, 5, 2.2 units along the x-axis and 5 along the y-axis. Then the dots that you see here, 1, 2, 3, 4, 5, 6. Those are the ones that I can describe with these arrows. And so the shortest arrow that you can describe in this system, or one of the shortest arrows that you can describe in this system, is this one that goes to the 3 minus 3 points. And in fact, in this system, if I zoom out, right, this lattice doesn't look like the lattices that you saw in the earlier slides. It's this kind of diagonal type lattice. So things begin to become a little bit less trivial than they are in the 0, 1, 1, 0 world. Now, one or two more slides here for you. Let's take these two vectors, these two arrows. So this one, the A1 is over 1 and up 1, and the B1 is over 2 and up 1. The shortest vector, the shortest arrow in this world that you can describe with these two is this one. That's a nice one. That's one that we are commonly familiar with. But how do we describe that arrow in terms of A and B? Well, it's not so simple because remember, we have to describe each dot in terms of a combination of a number of A's and a number of B's. Okay, so each dot has a different way of being described. And now, we're no longer calling this arrow 1, 0. We're no longer saying we go along here by a length of 1 and we don't go up. We go up by 0. Instead, we have to, let's do some different combination of A's and B's. And this one is minus 3A plus 2B. The idea with lattice cryptography is you give freely out to the world, to the public, these arrows. And what you keep as a secret is the description of the shortest vector in terms of those arrows, because that's hard to calculate.
Barry, we
Yes.
have a question,
Uh-oh.
and I'm gonna put it on the screen.
Okay.
Can you see it?
My presentation is covering that up. So it's all relative to the dots in the lattice. Mike, I'm not sure if I understand your question.
Well, maybe he will say more to it. And then there was another one that's asking a question.
How
This
come
one.
minus A plus B is shorter than A minus B? It is not. It's just one of the shorter vectors. When you find the terminology that people use is the shortest vector, what they mean is a shortest vector.
Ah, all right. And I see that the previous question said he meant the shortest path.
Yeah. The shortest line that you can describe with these vectors. So let's say that A, the first blue line that we're using to describe the lattice, is this one, and B, the next blue line that we're using to describe the lattice, is this one. Then the shortest non-zero vector, or a shortest non-zero vector, to find the description of it requires about 41 trillion calculations. This is not an easy problem to solve.
All right.
And real-world shortest vector problems use spaces of many more dimensions. So we're doing 2 dimensions, we're doing small numbers. But when this problem becomes large, it's what we call intractable. You can't solve it with a classical computer. You don't have enough time. Lord knows I'd love to live for trillions of years to be able to solve this problem with a classical computer. I don't think it's going to happen. For those of you theory heads like me, the shortest vector problem is known to be NP hard. Solving SVP, if you can solve it in polynomial time, then a whole host of practical problems will be able to be solved much more easily, much more quickly, much more efficiently than we know how to solve them now. Yes, and
all right.
okay.
Well, I think you had the question, so
my question had to do with the shortest vector. Mike, did I address your question or did I avoid it? Okay, he's not typing. Let me move on and we'll get back to his.
Just
okay.
maybe he
I
did.
believe you did.
Yeah.
Thanks. You know what he's answering is, I believe you did avoid it. Thank you. Okay. All right. Here we go. Oh, by the way, yeah, I'm. Oh, this is cute. Here's what you do. Here's what you do to generate such a problem. You create the blue vectors. Can you see the blue vector behind there? You create 2 nice ones, right? And you find out what the shortest vector is with those nice ones. And then what you do, I'm going to have to switch here. And then what you do is you find a different combination of blue vectors for which it's much more difficult to find the shortest vector. And that's what you deliver as your public key. You see, so the private key, the private key is going to be V1 and V2. and you'll know the shortest vector in the private key. But what you deliver to the world in order to encrypt the data is going to be these two vectors, where it's much more difficult to find out what the shortest vector is, and that's because these two vectors are what we call collinear. They're close to one another. The angle between them is very small. All righty. Let's talk about Java, shall we? Um, I don't know if you can read this slide because it's small and I cut it off here a little bit, but I just want to say that what's on what the at the heart of all this is the Java cryptography architecture. And the Java cryptography architecture is a whole bunch of um, packages that abstract away all the details, all the vendor specific details involving cryptography. And here's a list of some of the classes in the Java cryptography architecture. Um, Again, you may not be able to read it, but I just want to make make it clear that the Java cryptography architecture exists. And what is being defined in the new JEPs is elements, new elements for the Java cryptography architecture. So here are the JEPs that I want to talk about, or at least the JEPs that I want to mention. Um, they fall into three categories, even though there are five JEPs there. Um, One category is the key encapsulation mechanism, and the other is the quantum resist. Well, okay. One category is key encapsulation, and that's illustrated by one, two, three of the JEPs. So the idea with key encapsulation mechanism is it's a better way to transmit keys, private public keys, and get a secret key out of it. And it's part of the NIST quantum resistant specification. And uh, lattice based encryption is in the key encapsulation mechanism under the hood. So I want to talk about that for a bit. That's going to be the first thing that I talk about. Embedded within the key encapsulation mechanism is this idea called a key derivation function. And the key derivation function is a way of getting a generic secret key, a secret key that's not tailored to any particular vendor or any particular algorithm, and turning it into a particular key for a particular algorithm. And I'll talk more about that when I get to it. Finally, something that thank you, Susanna, reminded me of is an element that's not yet in Java is oh my gosh, I don't have it on this slide. Um, Digital signatures, and it's not on this slide. It's probably here. That serves me right. Okay, here we go. So just to make sure everyone's familiar with how this works, there's symmetric key and key exchange. There's symmetric encryption and asymmetric encryption. And symmetric encryption involves a secret key that both the sender and the receiver have. The key is used both to encrypt and to decrypt sensitive information. The sender uses the secret key to encrypt text, creating ciphertext. That ciphertext gets sent to a receiver who uses the secret key to decrypt it. The problem with symmetric encryption alone is that it's just kicking the can down the road. How do the sender and receiver both have the same secret key? The way that they have to do it is to send it across some channel, and that channel can be eavesdropped upon. So secret key encryption alone is not going to do it for us. What we need is to combine secret key encryption with private and public key pair encryption. So the idea here is that you The sender has a public key. The public key is only good for encrypting. The receiver, I'm going to switch to laser pointer. The receiver has both the public key, which they don't need to use, and a private key, which they can use to decrypt whatever's been encrypted by the public key. And so the receiver creates a public key, sends it, posts it in the New York Times so that any malicious actor can see it, but the sender in particular sees it, uses the public key to encrypt. Having that public key does nothing to help you decrypt the message. When they send the ciphertext to the receiver uses the private key to decrypt. And the reason that we don't use public private keys to send the sensitive information, the original message that wants to be sent between the sender and the receiver, is because private public pair asymmetric encryption is computationally expensive. So we don't want to take the entire text of some large document and try to use public key encryption on it. It's just too much for public key encryption. But what we can do is use public key encryptions to encrypt a secret key, which then can get sent to the sender. So how are we going to do this? Well, here's how traditional key exchange works. I'm going to call them not only not a sender and a receiver, but a company and a customer. The customer wants to send their credit card information to the company. That's sensitive information. You don't want to send it publicly. You want it to be encrypted. But first, what we want is for both the company and the customer to have the same secret key. So how do we do that? Well, again, I have to switch. Pointer options. Nope, don't give me a laser pointer. I need to click. So first, the company uses Java to create a public key and a private key. The private key is what they can use to decrypt information. The public key is what the customer can use to encrypt information. The company sends the public key along lines that can be interfered with and snooped upon to the customer. The customer has the public key. Again, the public key is not good for decrypting, so it's okay to have sent that. The customer uses the public key and creates a generic secret key. Now, that generic secret key, right? That's a secret key that, all right, let me talk a little bit more about that in a minute. The generic secret key and the public key are combined using an algorithm to create an encrypted, in this case, I said AES key, but the idea is using the generic secret key and the RSA key in traditional key exchange, traditional public-private asymmetric key exchange, the customer uses the public key to create an encrypted key, and that encrypted key is vendor specific and algorithm specific. And now they send that information because it's encrypted, they can send it back to the company, the receiver. And what does the receiver do? The receiver uses their private key and the encrypted AES key to create an AES key. And that shouldn't say generic secret key. It should say encrypted AES key. But let's leave it at that. Correct here. This should say AES key. All right. You know what we're going to do? We're going to think that this is AES key and this says AES key. One way or another, when all is said and done, what's left is an AES key here and an AES key there. So that's how traditional key exchange works. Now, the key encapsulation mechanism is different in a subtle way. The big difference is that it separates the randomness generation from the key distribution. It makes it easy to swap encryption algorithms in and out. And this is part of the new NIST standard for quantum resistant encryption. The idea now is, and I apologize for the confusion about generic secret key here. These are all AES keys. The idea here now is that the AES key, the vendor specific key, will not be sent from the sender to the receiver. Instead, it'll all be generic up until the last minute. Okay, so let's take a look at how that works. First, here is JEP 496, quantum resistant module lattice based key. I'm not showing you this so that I can talk about it. I'm showing you this so that you can refer to it back for future reference. Where am I? Give me a second. I have to look at my pages. Yeah, there's the JEP. Here we go. Post-quantum key exchange. So first, the company, the receiver, the one who wants to receive your credit card information, uses lattice-based encryption to create a public key and a private key. The private key is the shortest vector in this lattice situation, and the public key is basis vectors that are close to one another, that make it hard to find the shortest vector. The company sends the public key to the customer. The customer uses the public key. Wait, first what they're going to do is they're going to create a random value. And then they're going to use that random value, and another part of the new Java API called KDF. KDF is going to be used to turn the random value into a generic secret key. Now, that generic secret key is going to be a key that isn't supposed to be used for a particular algorithm. It's just a key that can be used for a particular algorithm, but we're not sure that it meets any of the specifications given by particular vendors and particular algorithms like AES. That generic secret key and the lattice public key will be used to create an encrypted random value, an encryption of the random value. That information, and only that information, gets sent to the company. So now what the company has is a value that's encrypted, but it's just a copy of the random value. That random value cannot be used as a key for encryption and decryption. It can't be used. That's all that's being sent. What's going to happen next is that the company is going to decapsulate. They're going to use the private key that they have to recover the random value, and along with decapsulation, they're going to use KDF to create a generic secret key. And once they have this generic secret key, they're going to use another part of the KDF algorithm to create a key that's specific for the algorithms that both parties have agreed to use. For instance, AES. So what we're left with now is a generic secret key. Now, the differences between the post-quantum key exchange and the traditional key exchange, those differences are subtle. But what you need to remember here is that what this does is it separates the random generation of values from the derivation of a key, which makes it easier to swap out one form of lattice-based encryption with another. And that's the whole idea here. That's what key encapsulation mechanism means. It means that when you're sending along the line here, what comes from one side of this diagram to another is not a secret key in any form. It's a random value from which both parties can make a secret key. So let's take a look at the code. And I'm looking at the time. The first thing that happens here is that the company creates a public key and a private key. There's the code to do that. I'm going to pause for a minute because code is nice. This is something that you couldn't have done before. Java '24. And you see that it's really not very heavy putting this information together. For example, you get an instance of a class that can generate keys. You give it the parameter spec. You tell it exactly what algorithm you want to use in order to generate those keys, and then you just generate them. And in this code, I say, just return me the public value so that I can send it to the customer. And this is all fair. I mean, look, one of the great things about these Java APIs is that this will work for any of the providers that we know about, any of the providers that we want to deal with, and any of the algorithms that we want to deal with. All this code is generic, not in the technical sense of the word generic in Java, but it's not vendor specific, and that's great. And so this is what you do now in order to generate a public private key pair in the quantum encryption world. So next, what happens is you take the public key and you send it over to the customer, and the customer generates a random value. They can do that any way they want. And then they use the random value to generate for themselves a secret key. Now, they're not going to advertise this secret key. They're just going to, at the same time, generate the secret key from the random value and encrypt that random value. And here's the code to do it. You get an instance of the key encapsulation mechanism. You get an encapsulator using the public key, right? Because all the customer has is the public key. They encapsulate it. That's when all the spinning happened, right? They keep a record of the secret key, and they also get an encrypted random value, which they send back to the company. What happens next? They send that information back to the company. The company uses Java code to do de-encapsulation. De-encapsulation means they get back the random value and they use the random value to generate a generic secret key. And what they use here is that other thing that I mentioned earlier called KDF. And I'll talk about that in a minute. That's called key derivation function. So the whole idea of KEM is we're not passing around keys, we're just passing random strings that can't be used as keys. In the end, both the company and the customer have generic secret keys. Very good. Here's just a look at the KEM Java doc. It has ways of getting an instance. It has ways of creating an encapsulator and a decapsulator. It's pretty much the code that you saw on the previous slide. Now, the key derivation function. This is a publicly known deterministic algorithm to derive a secret key from a random value. So the customer generates a random value and they encapsulate that random value, they encrypt that random value and send that encrypted random value to the company. The company uses decapsulation to get that random value back. How do both parties turn that random value into a secret key? That's with the key derivation function. And the key derivation function is an algorithm that we decided, we the Java community decided because of JEP 510 to add to Java's store of abilities. And here's the code that does it. I'm not showing you any complicated code in this talk because none of it is complicated. I'm not claiming, by the way, that encryption isn't complicated and security isn't complicated, just that this code is well, it's good stuff. It's easy to read. It's simple. It works for any vendor, any provider, any reasonable algorithm. And so what you do here is you get an instance of KDF, right? You add some salt and some other information, and then you use a chain of calls to get yourself a HKDF parameter spec. You get the parameters for the generation of the AES key, and then you derive the key using this method. Now, this is an example of KDF being used to go from, say, a generic key to an AES key. In the previous slides, we were using KDF to go from a random sequence of bits to a generic key. So you can use KDF for both, and this is now implemented in Java. All right, I
think this is a good moment for we got this comment.
I suppose it is vendor algorithm agnostic. Yes, absolutely. That's one of the goals of this whole program. It's one of the whole goals of a lot of Java APIs.
Awesome. Go
All
ahead.
right. Okay, let's make a digital signature. I'm running a little bit low on time, so I don't want to talk too much about this, but it's JEP 497, and there's some code for it. This is what's new in Java 25. The ability to use this algorithm that's part of the quantum resistant algorithm list, the ability to use this algorithm to generate a digital signature. The rest of the code here is stuff that you could have done in earlier versions of Java. But MLDSA 65 is what's new. And what we've got here is we generate a key pair from which we get a private and public key. We sign our message, in this case, Hello Java Champions Conference, and then the receiver of that can verify the message using the public key of the public-private pair. Now, do you want to do all this tomorrow? No, I don't think so. We should be able to do it tomorrow, but we can't. changing cryptographic algorithms is time consuming and work intensive. You have to, should I start reading these bullets? Identify what needs to be replaced, prioritize what needs to be replaced, um, decide on the architecture, key sizes, and other parameters. Once you've got your code in place, you have to do testing, you have to check for compliance. And a part of this that's often forgotten is you have to do training. So it's one thing to have all the code in place, but as usual, the people who are going to use this cryptographic structure have to know how to use it. And so we're not talking about days to implement this, we're talking about months. And I'm not going to say how many months because it depends on the organization, but the idea is malicious actors are harvesting our information now. So we better get started now doing the items on this list. There's no time like the present to begin the long and difficult and tricky business of replacing our current encryption algorithms with quantum resistant schemes. Thank you. Thank you for listening. I am here for questions of any sort.
All right. Any questions from the audience? Let's give him some time to write. We already have some comments. Let's say this.
Hey, thank you, Mike.
That was awesome. And Francois really liked the animations.
The reason I don't do the animations to be fancy. I do the animations because I find that it's the best way to illustrate ideas. When I'm thinking about ideas, I don't think words, I think moving parts. And so the animations to me are what the moving parts look like in my mind. Just to say it's not I'm not showing off. I'm just saying this is the best way that I could illustrate an idea.
Yeah, awesome. And I see that Vincent wants to do this question.
Is there a risk in the next years for bank accounts? It's absolutely. Absolutely. Why would there not be a risk in the next few years for bank accounts? That information is translated, is transmitted along lines that um, could be eavesdropped upon. Um, that sensitive information. If we're sending it now using RSA, then hackers are collecting that information and harvesting it. And when they get their nasty little hands on a quantum computer, they're going to want to decrypt it and find out what the information is in our bank accounts. And someone says, I'm still a bit confused about how to handle the ambiguity of multiple smallest lattices. The good news is that as a software engineer, you don't have to worry about that. I I I introduced that part because my background originally is mathematics, and so I like that stuff. But as a Java developer, not only are the particulars of particular vendors and providers buried under the hood so that you don't have to worry about it. Not only is it vendor agnostic, provider agnostic, it's very, very much lattice algorithm agnostic. Um, it's only the very, very, very careful specialists who are going to be worrying about the use of lattices. And if you're confused about it, send me an email. Here, put my slide back on the screen.
And this one. No.
bbird at drew.edu, right? Send me an email and feel free to ask me questions. Yeah. Other issues, other questions?
Any others? Well,
Okay. Well,
I
thank you so
think
much. Thank you, everybody. Thank you, Susanna.
thank you,
Thank you,
Barry. It's
Ken. Thank you, Java J Champion conference organizers.
Thank you for this incredible presentation, and
Okay.
thank you all for coming to this session. And well, I wish you all a good night.
And if you're in the East Coast, United States, stay warm. It's going to be a rough weekend.
Oh boy. Okay. Well, bye bye, everybody.
Bye.